Dr. Scott Rickard is the co-head of the Data Strategies Group at Citadel. Prior to Citadel, he was the SVP and CTO for data science at Salesforce, the CEO of the hedge fund Probability Dynamics, and a professor in the School of Electronic, Electrical, and Communications Engineering at University College Dublin, where he was the founding director of the Complex and Adaptive Systems Laboratory. Prior to UCD, he worked for Siemens Corporate Research, applying machine learning to industrial research problems, including developing a source separation tool used by the FBI. He has a BS in mathematics, a BS in computer science, and a BS in electrical engineering from MIT, as well as an MA and a PhD in applied and computational mathematics from Princeton University. His research interests include machine learning, computational mathematical finance, sparse signal processing, time, frequency, and scale analysis, blind source localization and separation, multi-user frequency hop communication systems, COSTAS arrays, and ugly music. So please everyone join me in giving a warm RSI welcome to Dr. Scott Rickard.
Thank you for the introduction. As was just mentioned there in that kind introduction, I've had a very varied professional career so far, and I wanted to share some of the reflections of how I think that high impact innovation can occur. And there's basically 4 key thoughts, themes that I want to organize this presentation in. The interesting stuff happens at the edges. If the problem is unsolvable, redefine the problem. Diversity is the only free lunch, and communicate the big idea. So diving right in here, the interesting stuff happens at the edges. Okay, so before there was North Korea, and before there was Putin, I don't know why this is going there, before there was, pause it there, before there was Osama bin Laden, the most dangerous person in the world was Saddam Hussein. And this is the first Gulf War and the second Gulf War. Saddam Hussein basically mined the Persian Gulf through a bunch of dumb mines that if they hit a ship would sink the ship, and challenge the world to basically to continue to sail through the Persian Gulf. And I, at that time, was a graduate student working at MIT, and I was working at Draper Labs, which is, I guess, nearby to RSI, and was working on a project that was called the Intelligent Sonar Buoy Project. And the challenge was I was in charge of designing a series of sonar pings that helicopters would fly over the Persian Gulf and throw out mines into the Persian Gulf. Sorry, throw out sonar buoys into the Persian Gulf. And the sonar buoys were to form a network where each sonar buoy would have a unique ping, and all the sonar buoys would be listening to each other. So the pings couldn't interfere with each other, and they had to have a ping that would encode their GPS location. The pings would also have to be a good sonar ping in general. In researching different sonar pings, I became familiar with the research of this person here, who's John Costas. He was also affiliated with MIT, but he was a researcher at GE, and he had discovered a series of sonar pings. He was in charge of analyzing these new sonar ping array system that was on a destroyer. And the system had failed fantastically, and he was in charge of figuring out why it had failed, and then in charge of fixing it. So his idea for generating a new sonar ping was based kind of on musical theory, if you will. His idea was to maybe if a random sequence of notes on a piano might make a wonderful sonar ping. So he started thinking about taking permutations of numbers, which would then appear like a random sequence of notes on a piano. So not random because, of course, you're only going to play every note once, and was wondering if the relationships between each pair of notes was different, if that would make a good sonar ping. And it turns out that it would. And here's a quick review of sonar ping theory. So the pattern in the upper left is what's known as a down chirp. In sonar, you send out a tone or a sequence, some kind of a pitch sequence, and you then listen for the returns of that sequence. the longer it takes the sequence to come back, the further away the object is. The higher the pitch is, that means that the object and you are moving toward each other. If it's a lower pitch when it comes back, it means that you're moving away from each other. So just based on that one return, you can know not only the range to a target, but also its relative motion to you. So this on the upper left hand would be a down chirp, would be like a if you were to play it on a piano, glissando from the upper notes to the lower notes. John Costas invented the sequence to the lower left, which would appear like, which appears like a random sequence of notes. It turns out that this is not a random sequence of notes. This pattern of dots on the grid here, by the way, the x-axis here being time, the y-axis being frequency. So very much like musical notation. The pattern here is very particular. You notice that the first two notes have a relationship that they would be up if they were on a musical staff, maybe up like a semitone. They'd be like boom, boom. And there are no other pair of notes that are adjacent to each other which have that relationship. And it turns out that any note separated by I steps will have the same J jump in them. So this is a pattern-free, a repetition-free pattern. It's a pattern-free pattern to have an oxymoron. How you then look for the returns of this is you can think of taking a transparency of the same pattern and shifting it on top of itself, counting the number of dots of overlap. That's what you do when you're looking for the exact timing of the return pitch. If you're shifting it up in frequency, you're going to know that it's coming toward you. And this pattern here has this ideal thumbtack ambiguity. Regardless of the shift of the pattern, I only ever see all the notes hitting with each other for a perfect overlap. For any other shift, I'm either going to get 0 or at most 1 dots overlapping with each other. There's always, of course, for every pair of dots, I can shift that exact pattern and get those 2 dots to overlap. But all the other dots will miss each other because this is the defining property of a Costas array. This and the fact that it is a permutation, that I do have 1 note per column and 1 note per row. That's unlike the pattern in the upper right, which has this, kind of shark fin ambiguity pattern. If I shift up 1 and over 1, I'm going to get n-1 notes, up 2 and over 2, n-2 notes. So there's this ambiguity problem right along this time frequency and the time frequency axis here, where if there's noise as well, I can't really identify where the peak is, where it's quite obvious from the thumbtack on the lower right exactly where the peak is. Now, where do these patterns come from and how do we generate them? Well, Costas wrote a letter, this is back in the 60s, he wrote a letter to Solomon Golem, who was much younger at the time, who's on the lower right here, who was a USC, University of Southern California, discrete mathematician, professor, and asked him if he could just point him to the right references that would describe these patterns. These patterns, again, that would have be a permutation that would only have at most 1 repeated common difference between pairs of in the array. Solomon Golem got back to him later in the summer and said, oh, it was a very interesting problem that you proposed there. It turns out that I couldn't find any references. So I talked to some of my colleagues, and he then described 2 different ways in which we can generate these arrays based on prime number theory, based on Galois field theory, which is the gentleman in the upper left. Many of you may know that Galois is quite famous for 2 things. He's famous because he invented effectively a finite field theory or prime number theory, of which like modern communication theory and encryption are largely based on. So most of the practical mathematics that allow us to communicate securely or communicate at all with error correcting codes, as well as all the codes that allow computers to actually work, are based on Galois' mathematics. He's also famous because of the way that he died. So he got into a argument over the honor of some woman which he was defending, and he was challenged to a duel, and he was a much better mathematician than he was a pistol marksman, and he got shot in this duel, and over the 3 days that it took him to die, wrote down all of his mathematical ideas frantically, and they found their way to the desk eventually, several years later, of Louisville, who recognized the brilliance in Galois' hastily written letters, and he eventually filled in all the gaps, the significant gaps in all the proofs that Galois had basically said all these things were true and didn't actually prove most of them, but Louisville was so talented he was able to actually prove them all and gave all the credit to Galois. This is the reason why that we know how these patterns exist. There's actually elementary school mathematics can generate these patterns. So for example, multiplication, it turns out that 89 is a prime number. So around a prime number, each prime number has what's called a generating element, which is an element when raised to successive powers, taken modulo the prime, will generate all the numbers between 1 and 1 less than the prime. So 3, it turns out, is a generating element, a primitive element, sorry, of a Galois field with 89 elements. 3 to the 0 is 1, 3 to the 3 is 3, 3 to the 1 is 3, the 3 squared is 9. I keep on multiplying by 3. When I get to something which is larger than 89, I take away 89s until I get back to down below 89. So this pattern generates this exact sequence here, 1, 3, 9, 27, 81 to 65, and so forth. And it turns out that this is a Costas array. This is one of the 2 generating techniques that Solomon Golem proved. And it turns out that no one has really found anything really interesting since this initial work by Solomon Golem, which was published in the 80s. A number of researchers, myself included, have found bizarre ways of perturbing some arrays to find, to kind of play with the edges to find some other patterns that indeed are Costas. I've led several international efforts to enumerate the number of Costas arrays. You might find it surprising that the number of Costas arrays as a function of n is not monotonically increasing as n gets larger and larger. You might think that there's more and more of them. It turns out that they peak at a local peak at 16, and then they begin to fall. No one has ever found a Costas array of size 32 by 32 or 33 by 33. We do know that they exist, an infinite number of them exist because there are an infinite number of primes, and therefore there are an infinite number of Costas arrays. If you want 100 million Costas arrays, I'll find a super large prime number that has enough primitive elements to generate exactly that number that you require. Right now, it's not known whether they exist for all n. That's probably the biggest open question in this very subfield of mathematics. It's not like the world's going to stop spinning whether we find one at 32 or not 32, but there are certainly a certain segment of mathematicians which will be very interested in this beautiful or perhaps ugly theory if the pattern you think here is beautiful or ugly. While I was at MIT, I seriously considered studying music. I sang and played trumpet and loved music theory and composition, and was taking every music class I possibly could. And I learned about modern music of Schoenberg. And Schoenberg talked about the emancipation of the dissonance. So for anybody that's ever listened to Schoenberg, he writes truly ugly, shitty music. It's just amazing how bad it is and how painful it is to listen to his music until you listen to it enough that you might convince yourself that it's not so bad. But what he really wanted to do is he wanted to free music from its tonal center. So when I was learning about Schoenberg, I thought, oh, like if Schoenberg knew about Costas and Costas arrays, it's not that you want to play each note like once on the thing. You want to play notes in an order so that there's no pattern whatsoever to them. So I knew that Schoenberg really wanted to write actually Costas arrays music. So I wrote that music actually when I was a professor at University College Dublin. This is one of several pieces that were written. This is called Costas Golem number 1, the perfect ping, and it is based on the pattern that you just saw, the 89 being prime, thankfully, because there are 88 notes on a piano. So this was written for a piano. And then a couple of years later, I was volunteered to give a TEDx talk in Miami when I was living in Miami, and found a pianist to actually play this piece. So we had a world premiere, and if the sound is working here, this is actually the TED Talk, and this is the world's ugliest piece of music. up in a second. Clearly, you can hear music. It's odd if you can hear music. So, what's my favorite part? Right. Of course, if you made a mistake, no one would know. You might notice, of course, that the notes are not played. But here comes my favorite part. There it was. You might note that he's not playing all the notes in a common with a common rhythm. The notes are actually separated in a pattern what's known as a Golomb ruler, which is that the Golomb ruler never measures the same distance twice between any pair of notes as well. So it's truly like a doubly pattern free structure here. This was also somebody named George Sticka actually wrote an entire symphony based on the and this is me with John Costas shortly before his death. Actually, he lived outside in Waltham, Massachusetts, and shortly before, I'm a kind of a Costas stalker. I found him and went and met with him and found out the whole story of the invention of the Costas array. He's actually much more famous for the invention of the Costas loop, which is a phase lock loop for communication systems. It was actually a couple of years after I gave that TED talk, I got John had been dead for a decade. I got an email from John, which was kind of confusing. And it turns out I had misread the email. It was actually from Joan Costas, his daughter, who saw the TED talk and saw the picture. And she's like, "You were in my dad's study." And she didn't know about anything, as most daughters do, anything about John's work. And she was so pleased to find out that there are, dozens of mathematicians, not a huge number, but there are dozens of people obsessed with these patterns. And if anybody on the call would like to discuss with me what my current research into these patterns, I'm actually working on a new set of code that I hope will finally be able to push through to 32. I'd be more than happy to talk to them about that. The point being there that the interesting stuff happens at the edges. Why did I mention that theme? Here we have music, we have electrical engineering, we have sonar theory, we have prime number theory, and when all of those things come together, you come up with something which is, in my opinion, truly innovative, if ugly, but still innovative. On to the second theme. So I worked for a decade at Siemens Corporate Research in the Princeton area and also in Munich. And my boss at one stage gave me the problem of solving blind source separation, which is also known as the cocktail party problem. So the problem here is when many people are speaking at the same time, can you separate out one of the voices or each individual voice from the other voices? We know this is possible because oftentimes in a cocktail party, you can sit there, you can't listen to everybody at once, but you can certainly try and focus in on one individual. And it's kind of amazing that we can do that because we know from basic mathematics that in order to solve an equation or for unknowns, I need as many constraints as I have unknowns. So if I have like 2 unknown sources, I would need 2 kind of constraining equations. If I have 3 unknowns, I would need 3 constraining equations. And it turns out that the humans have 2 constraining equations. I have my left ear and my right ear. Each of those provides a kind of a constraint. And yet I can separate out many people speaking at the same time. Not at the same time, but I can at least focus in on one person. So clearly we're not doing kind of matrix inversion. We're not doing simultaneous equation solving. If we were, we couldn't do it. I got 2 equations, I got 10 unknowns. There's no way I can listen to any one thing. I'm never going to be able to, I can cancel out one of the unknowns, but I'm going to end up with a mixture of 9 things. So clearly our ears are doing something different. So just to kind of put this back into musical terms, here I have 2, I'm actually talking to you from Dublin, Ireland right now, where it's 22 minutes after midnight. But here's 2 Irish ditties that, and their music, and I've chosen to color one of them red and the other one blue. And if I overlap these 2 things, as if they're being mixed in my ears here, if you read the words or try and read the words, clearly you can't make out anything. But the reason why I'm presenting this in musical form, to use the musical analogy, is that if I actually look at where the notes are occurring, the notes are kind of already separated. I can see blue notes and I can see red notes. Occasionally I get a purple note. I think there's a note in the lower left there. There's a purple note, and in the middle lower one there's a purple note. But for the most part, the notes are already separated. Right? I just need to figure out which note is which, right? And it turns out that there's ways that we can do that. In the time frequency domain, if I have my two ears and my voice, if I'm speaking from this side, my voice is going to hit this thumb before it hits this thumb. It's going to be louder and earlier here. And if I'm right in the middle, it's going to be simultaneous and equal loudness. And over here, it's going to be earlier on this thumb and quieter there. And specifically, if my ears are faced one direction, I can also get kind of, and if I have these weird pin-A formulation here, I can kind of learn that there's, even other dimensions based on the specific ways that the loudness is affected from one ear to the other. So I was actually, it was during my doctoral oral examination, and I had been working with my office mate at Princeton and my colleague at Siemens for many months on this problem, trying to figure out how to solve it. And Bradley Dickinson, who was a professor at the time, was talking about the time frequency domain, and he was put his hands up like, oh, you have some music, and here's like the pattern of the music, and he overlapped his hands like this to me. And at that moment, I realized that we had solved the problem, right? And so I was like, Professor Dickinson, I need to go back to my office and write this stuff down because I've just solved something. And I was like, are we done? And he's like, I suppose we're done. So I went back and I showed this to my office mate at Princeton. And he's like, we immediately knew what we needed to do. You go into the time frequency domain, and then you take for each pair of notes, this is my left ear's note, this is my right ear. For each of the time frequency points, I take the ratio of the 2 points. Those ratios should cluster around certain delays and certain relative amplitudes. And this is a pattern for 10 different sources. This is actually for frequency up communications, but it's the same for speech as well. In one dimension, I have relative amplitude, and in the other dimension, I have relative delay. And here I can see that there are 10 sources. I've clustered the energy of the notes that are appearing based on their relative amplitude and delays extracted from the ratio of all the notes that I see. And then if I want to then reconstruct each of the individual sources, all I have to do is say, put a circle around one of these things and say, all of the ones that occurred with this relative delay, with this relative amplitude, those notes I know. I don't even need the second mixture at that stage. I can just look at the first mixture and I can mask out all the other notes and just play back the notes that I want to play back. So this is a tool that I built in MATLAB that we sold to the FBI. The reason why we sold it to the FBI is because it turns out that the FBI has lots of recordings of people saying, in many cases, doing bad things or saying things about bad things they're about to do or have done. These mixtures, like you can imagine in the movies, usually occur with loud noises in the background in crowded places. They tend to be very smart about where they have these communications. And they often do things like turn on water or music while they have these communications to make it very hard to separate out the signals. The specific case that we were originally challenged to solve was that a woman had been found stabbed to death on her kitchen floor. They had found a recording in a neighboring room, a video recording actually, but the person they think committed the crime never actually showed their face in the video, but had put on Michael Bolton music, and then went into the kitchen and had a large fight with the woman, not over the fact that they didn't like Michael Bolton, but then at some stage you can hear this big crash of dishes, like someone had thrown things, and then you can hear some truly blood-curdling screams. And then you hear somebody run away, and then over several songs, this woman unfortunately passes away. It took me several weeks to recover from listening to this. It's amazing. The FBI guys, after we listened to the recording a couple of times, were like, "Let's go grab lunch," and I needed to breathe into a paper bag at this stage. I mean, the woman had been dead for several years at this stage. They were still trying to solve the crime. What we were able to do using this tool is we were able to essentially turn off the music and only allow her voice to pass through. And at one stage, she did said, "I've had enough, Jabbar," and that was enough. Jabbar actually was already in jail for a related crime, and this was enough to charge him with murder as well. So this is a demo that I gave of this. Okay, that's good. Thank you. Okay, let's see if this worked. I'm sorry. I'm generating the histogram already with the wrong parameters, so that's going to kind of, oh gosh, I can see perfectly actually. There's one there, I think, and one there, and one there. This actually might work. Resources. Which should be very gratifying. And in real time, effectively, get this.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Me llamo Plaza Cuerayartas, crecí en México DF. Estamos hablando todos al mismo tiempo y creo que...
Okay, so that's certainly another language.
Mary Hulk na Salandong, Tony Tony, Valley Archaea, agus ag Hyper UCD Castle, and Valley Archaea, Taw, Sundown, or an show. Very difficult to speak Irish when there's Russian and English in.
Okay, he was speaking Irish actually there, and they were all laughing because he was asking things like everyone knows, like the Lord's, Hail Mary, full of grace, and they also know where's the bathroom. He was basically saying, what you would learn, from and remember 40 years after learning Irish. So that's the source separation algorithm, and then the third channel was actually Russian, and you could separate out the Russian there as well. But the amazing thing is that this can separate again many more unknowns than the two constraints that you have in the 2 years. So we also applied this to several other domains. Which is here I have, this is, you're going to see here, a beating heart, and this is a multi-channel stethoscope. We had a project with St. Vincent's Hospital here in Dublin to diagnose early stage coronary artery disease. So here we have the beating heart, and there's actually a catheter in there, which is injecting a dye. And there's a small constriction right here. This procedure is very invasive, as you can imagine, because they're sticking a catheter in through a leg vein all the way into your beating heart to inject this dye. And there can be lots of complications that's caused by this. And what we were doing by having the multi-channel stethoscope was to see if we could listen in specifically to the turbulence of that flow and localize it without having to put patients through an invasive and potentially dangerous procedure. So another problem that we attacked with this is based on that. We thought, well, we could also, what other environments is there flow or turbulent flow or increasing flow is interesting. And it turns out that predicting volcano eruptions is something which is interesting. So I worked with a geoscientist, and we wrote a paper on source separation on seismic data where we could localize and identify magma flow, increasing magma flow specifically on active volcanoes. So the important theme here again is if the problem is unsolvable, right, redefine the problem. And in this case, we redefined it in a time frequency, in a musical context. And in that context, the separation problem, rather than simultaneous equations trying to cancel unknowns, became one of identification. They were already separated in this other domain. It just became a labeling problem. And the labeling we could get from the second channel, which gave us a little bit of side information. If you work in finance, you'll eventually hear this phrase that diversity is the only free lunch. I accidentally started working in finance based on my background. You'll notice that nothing in it suggested that I was interested in finance at all. I was trying to raise money for this large complex and adaptive systems laboratory, which I was running, and was talking to some high net individuals in Dublin, in Ireland, and in convincing them to donate $100 million to the university to build a new science block, and ended up convincing myself that I should go work for them. They had some guys thinking about predicting financial markets and herd mentality. So I eventually basically went and working for an Irish billionaire, and then eventually founded a hedge fund with him, which is still trading to this day, 10 years on. But diversity is the only free lunch is something you'll hear lots of vapid statements in finance. The trend is your friend. mean reversion, which are the opposite of each other. But diversity in the free lunch is actually something which is quite powerful. And what does that mean in finance? Well, in finance, the only metric that really matters, especially if you're a hedge fund, is your Sharpe ratio. And in general, your only metric that really matters if you're an investor is how much return can you get per unit of risk. So if you're naive in finance, you think, oh, how much did you make? Did you double your money? Did you triple your money? But you don't really want to know that number. What you really want to know is how much money did you make relative to the fluctuations of your money. Your basically normalized return, your risk over your return is the metric of choice. So for a Gaussian process, if your expected return is R and your standard deviation is S, the Sharpe ratio is R over S. So if you have some kind of meandering process which is growing, you take the standard deviation, you take the average return, and you divide the two, and that gives you your Sharpe ratio. If you can get a Sharpe ratio above 1, you can make infinite money basically, because people will give you money to invest on their behalf. If you can get a Sharpe ratio, 2 or 3 or 4 or something, then you'll be one of the most successful hedge funds on the planet. So it turns out that if I can get 2 independent ideas that their returns are independent of each other, and I just simply sum those 2 processes together, the Sharpe ratio will grow with the square root of the number of processes, so square root of 2, so about a 40% increase in terms of my Sharpe ratio. So if I had 16 independent processes, I'd get a 4x multiplier on my Sharpe ratio. So you don't have to get actually a 1 idea that gets you a Sharpe ratio of 1. I can get 16 ideas that get me a Sharpe ratio of 1/4, 1/4, and that will get me all the way home. And it turns out it's much easier to get Sharpe ratios less than 1 than it is greater than 1. Now, getting independence might be difficult, but this is the idea. So just to kind of put this in terms of financial language, here's 10 independent Gaussian processes. This is just generated in MATLAB random things. And the black line there is the sum of the 10 of them averaged out, the average of the 10 of them. I mean, you might look at here and say, oh, the blue one was the best one, but then it had some bad luck there. Oh, then it came back. They all kind of end at the same place though. And these are, literally just random sequences. So you might say, well, the black one doesn't look that much better, right? Now, but rather than normalizing for total return here, if I just look at normalizing for the variability in the return, this is the same 10 plots. So the 10 plots are at the bottom there, and now I've normalized toward the variance so that the variance is the same, and standard deviation is the same. And now I'm making 450 times my original wealth, where each of the other ones, for the same amount of risk, are making significantly less. So this is the diversity game. When they say diversity is the only free lunch in finance, it really truly is a free lunch, and it's something that you should exploit. Not only necessarily in finance, but I found in everything that you do. And what do I mean by that? For this hedge fund that we created, we would bet on multiple strategies. One being the trend is your friend, which is if the market goes up, it will continue to go up, or if it goes down, it will continue to go down, and also reversion to the mean. If it goes up, it's going to go down. If it's going to go down, it's going to go back up, right? So we would bet on both of those strategies and try and figure out which one's working in which environment, on which time scale. We also invested in diversity in time scale, seconds, minutes, hours, and days. We also invested in equities, bonds, currencies, metals, energy, softs, like everything from lean hogs to gold. And when you layer on top all of those things at the same time, you can begin to get things the Sharpe ratios that are 1 or north of 1. But outside of strategies, you can also think about this when you're building a team. So here's a list of all the degrees for the 8-person hedge fund that we created, and they're all kind of related, but still. We had people from theoretical physics to computational physics to high performance computing, electrical engineering, mathematics, computer science. The point being that when you have a team with different backgrounds, I would actually call this now, based on the other teams that I've worked with, to be quite narrow in backgrounds. But diversity and expertise means that when you're trying to solve problems, there's always somebody that can identify what problem you're working on is similar to something in their background, and they can apply that unique tool in their toolkit to solve it. So in my current team in Citadel, I have everyone from network theorists to information theorists, mathematicians to finance people. Actually, very few finance people. We have most of the people that are on our team actually did not come from a finance background. They came from hardcore technical backgrounds. And it's in that diversity that we can provide truly unique solutions that the investment professionals find very useful. So again, diversity is the only free lunch. And the final big idea or theme that I'd like to talk about is communicate the big idea. So I used to teach Introduction to Electronic and Electrical Engineering at University College Dublin, and I used to ask my first year students in the first lecture, what is the most impressive thing that mankind has achieved, right? And people would call out, the invention of the computer, the cell phone, YouTube, the web, various things. And I still think today, the most impressive thing, if you look there, is the fact that we have put human beings on the earth and returned them safely to Earth. Especially when you consider the fact that we did that before I was born in 1969. It's, with the power, of computers that, my little Wise, whatever Fitbit thing here that cost $25. That's really super impressive that we were able to do that. And when the moonshot was occurring, as many of you know, not everything went well. There were tragic deaths with Apollo 1 and the 3 astronauts burning up on the test pad. But there were several setbacks, and not all of them were tragic in human terms, but they were several $1 billion over budget, and the Congress sent a blue ribbon panel down to Florida to see whether it was still worthwhile in proceeding with this grand vision. And one night around midnight, this is a slightly apocryphal story, but it still makes the point. One of these panel members was walking through this large hangar, and he saw somebody with a NASA emblem on who was walking through it at the same time, and he asked him, "Oh, what are you doing here so late at night?" And the gentleman responded, "I'm helping put a man on the moon." And then he asked him a little bit further what he was doing, and it turns out he was a janitor, right? So this guy went back to Congress and said, every single person knows what they're doing down there. They are helping put a man on the moon. They're going to be successful. And they went forward. And of course, they were successful. This is an important story because when we were working on the HEART project, and we were looking at that data, it turns out that almost every patient that was tested around 5 p.m. each day was, we believe, suffering from incredibly bad coronary artery disease. We later discovered that around 5 p.m. every day, this happened. This is somebody who's coming in and waxing the floor. To drive the point home that the janitor needs to know what it is that you're doing. Everybody in your organization has to understand what it is that you're trying to do in order for you to be successful. And thankfully, 2 of the organizations that I've had the pleasure of working with, Salesforce, I'll actually go to Salesforce first so I can end with Citadel. So Salesforce is a company that helps salespeople better manage their customers, which as a mathematician, I really have no interest in whatsoever. And the only reason I went to work at Salesforce is I wanted to actually work for kind of a big data company. I'd never been in the Valley. I had kind of run out of things to solve at the university. So I was interviewing at Salesforce, and somebody in the company told me that they asked me why I wanted to come to Salesforce. I said I wanted to work for a big data company. And this guy said, Salesforce isn't a big data company. It's a trust company, right? And I thought to myself, I want to come work there just to know what the hell that means. That's such an interesting statement. But Salesforce has an ethos. They have trust in their customers can trust them with their data. Every meeting begins and ends with that statement. They never do anything ever to violate that trust, which makes it really hard to do data science in a company where you can't look at the data, which is another reason why I wanted to go there, because it's really interesting. There's a lot of interesting data science problems. And how do you do data science when you cannot look exactly at the data all the time? And that was why it was really interesting to work at Salesforce. When I came and then was thinking about another shift of gears and working at Citadel, I told them my trust story at Salesforce, and I asked what the ethos of the company was at Citadel. And I was told that it's winning. And I thought winning, I'm like, you know, as a mathematician, as somebody who wants to solve problems, I was like, winning is not good enough for me. I sat there a little bit disappointed. And then Pong said, it's winning with integrity, right? And that's why I joined Citadel. It's the with integrity piece that I joined with Citadel. That with integrity is not lip service. Every single meeting begins and ends with integrity, personal integrity, professional integrity. It is the safest work environment I've ever worked in. There is no inappropriate behavior. There is, especially in finance, where it's